In this video, I want to discuss permutations, which is a fancy way of saying the number of ways in which a set of things can be uniquely arranged. Notation for permutations can be written in two ways. So the first way, with the capital P and then the parentheses n comma r, and the second or more standard way with the n, capital P, and then r, with the n and r as subscripts. What this equals is n factorial over n minus r factorial. And if you aren't familiar or haven't reviewed factorials in a while, then a factorial, I'll give you an example. We'll just do 5 factorial. That's going to be equal to 5 times 4 times 3 times 2 times 1. Okay, to make more sense of this equation, let's do a couple of practice problems. Example number 1, you have 6 people but only 3 chairs. How many unique ways can you fill each chair with a person? There's actually 2 different ways to solve this, one using the equation and another to use the fundamental counting principle. Depending on how the answers are set up on the ACT will determine which way you should do the problem. And I'll show you what that means in a minute once we solve it. So let's use, since we're just learning permutations now, let's use the equation. So this would be 6 permute 3. And if we plug that into the equation, we have 6 factorial over 6 minus 3 factorial. And of course, 6 minus 3 factorial, it just is 3 factorial. So this will equal 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. And you can see that we can cancel out the 3, 2, and 1 from both the numerator and the denominator and just get 6 times 5 times 4, which is equal to 120. The other way to do this, which I find a little bit easier, is using the fundamental counting principle. So that first chair, we have 6 options to fill it. So we just take that 6. Then in that second chair, now that we've removed one person, we have 5 people left. So we have 5 choices for the second chair. And once we've filled that chair, we have 4 people left to fill the third chair. And we get 6 times 5 times 4, just using that fundamental counting principle. And that'll give us the same answer as 120. Now, on the ACT, if one of your choices is 120, then that would be your correct answer. However, sometimes they plug in the formula and don't finish solving the problem with a number. So they may ask you which represents how to solve the problem, in which case you might get 6 factorial over 6 minus 3 factorial, and that would be your answer. Okay, let's do another example. There are 6 people in a room. They are told to shake the hand of every other person in the room once. How many handshakes are going to occur? So this is going to be 6 permute 2, which equals 6 factorial over 6 minus 2 factorial, or 4 factorial. And of course, I can write that out, or we can plug it into a calculator since we have the calculator. So let's just plug it into the calculator and do it the quick way. So that'll give us 30. However, 30 is not our answer. And my bet on the ACT, if they had a question like this, they would have 30 as one of the choices in there to confuse you. The reason why 30 is incorrect is because we're forgetting something. In the question, it states they are told to shake the hand of every other person in the room once. So this number is actually going to double the number that we want, because with the permutation, it states that order matters. But since everyone's shaking the hand of everybody else once, if person 1 shook person 2's hand, person 2 is not going to return and shake person 1's hand again. So we're double counting the handshakes. So our final answer is going to be 30 divided by 2, or 15. Okay, there's an easier way to do this problem as well that doesn't involve permutations at all. So will draw that out for us. So I'm just going to label the people here as person 1, 2, 3, 4, 5, and 6. So person 1 is going to go through and shake person 2, 3, 4, 5, and 6's hands. So he's going to do 5 handshakes. Person 2 has already shook person 1's hand, so person 2 just needs to shake the hands of person 3, 4, 5, and 6. So that would be 4 handshakes. Person 3 likewise will not need to shake person 1 and 2's hands, and will just need to do the last 3 people, and so on and so forth. Person 6, of course, will not need to initiate any hand contact with anybody because everyone's going to come to person 6, so that would be 0 for person 6. And we can simply add up the total number of handshakes, 5 plus 4 plus 3 plus 2 plus 1, and that'll give us the same answer of 15. All right, final example. How many unique ways are there to arrange the letters in the word banana? Okay, in this example, we're going to take, we have 6 letters, and we're going to permute all 6 spaces. So 6p6. So that's just going to be 6 factorial over 6 minus 6 factorial, or 0 factorial. And by convention, or definition, 0 factorial is just equal to 1. So it's just going to be equal to 6 factorial, which is equal to 720. However, if we were to put 720, we would be incorrect, because we're looking for unique ways to arrange the letters, and A, we actually have 3 A's, and N, we actually have 2 N's. So every time we have an A, it can be switched with another A, or even another A, and it would not be a unique combination, because it would be the same thing. So how do we account for that? So what we need to do is we need to take, we have 3 A's, so we can do 3p3 to account for the A's, and for the N's, since there's 2 of them, we can do 2 permute 2. And we'll see that 3 permute 3 is just 3 factorial, and 2 permute 2 is just 2 factorial. And 2 factorial is just 2, and 3 factorial is 3 times 2 times 1, which is 6. So those are the number of ways that we can arrange the A's and the number of ways that we can arrange the N's. So we have 720 total ways to arrange the letters, and then we need to divide that by 6, and then divide it by 2 to give us the total number of unique ways to arrange them, considering the fact that we have duplicate letters. So 720 divided by 6 divided by 2, or 720 divided by 12, is our final answer, and that should be 60.